Welcome to AI for Good, the leading, action-oriented, global and inclusive United Nations platform on AI. Organized by the International Telecommunication Union, the United Nations Agency for Digital Technologies, in partnership with 50+ UN sister organizations and co-convened with Switzerland. The goal of AI for Good is to unlock AI's potential to serve humanity. In today's AI for Good event, we are counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished facilitators and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
So hi, welcome everyone. My name is Konrad Philipp. I'm working for Alice and the Alice unit in Jena, Germany, and it's my pleasure to introduce you our speaker of today, Tomasz Chiński. He is a full professor at Warsaw University of Technology and the head of the computer vision lab there. And he received his PhD in machine learning from EPFL in 2014. And Tomasz has an industry experience at Google, Qualcomm, and Telefonica. And he was also a co-founder and leader of technology companies and startups. He is a reviewer and area chair for major journals and conferences like CVPR, ICML, and EURIPS, where he also received last year in 2025 the Best Paper Award at EURIPS. And he is a senior member of IEEE and a fellow of the Alice Society, as well as the director of the Alice unit in Warsaw. And today's talk is about zero waste machine learning. And Tomasz, the floor is yours.
Thank you so much, Konrad, and thank you for the invitation. It's a great pleasure to give a talk about zero waste machine learning, which is actually the main topic of my research, and I hope it's going to be inspiring for you, and also you'll find it interesting, especially in terms of AI for Good, which is very, very much at my heart. As Konrad mentioned, I'm affiliated with Warsaw University of Technology and also IDS Research Institute. And just to briefly kind of introduce you to our institute and our ecosystem in Warsaw, we were established as a Alice Unit Warsaw in 2023, so a couple of years ago. We already have 16 members. And there are 3 institutions: Warsaw University of Technology, University of Warsaw, and IDEAS Research Institute hosting this unit. And so far we received 1 EURIPS Best Paper Award, but that's just the beginning. So if you want to find out more, feel free to visit our website and also take a look at the video that shows the last EDS. Alice Doctoral Symposium we hosted in summer 2025. All right, but getting back to zero waste machine learning, the topic of today's talk. I asked before getting prepared for this talk, I actually asked ChatGPT what is what is the inspiration that I can talk about, and what is interesting, it already gave me the reference to the projects that we were working at IDS in the last couple of years. And that's exactly a good abstract. So if you fall asleep during the talk, this is pretty much what you should remember. That zero waste machine learning aims to leverage computation reuse, knowledge accumulation, and conditional computations rather than simply bounding resource usage. This is like a one line that defines what we work with and why it is important. Well, so you probably know a lot of ways where computation, especially using machine learning, uses a lot of energy. Data centers that are spread all over the world, and they're building hyperscalers, building them quite a lot these days, even more. This is the first place where even a tiny little saving on computation can mean a lot because of the size of this industry. The second inspiration and use case where our research can be put in practice for good is this detector of particle collisions at CERN. This is actually a picture of one of the detectors I work with as part of CERN users. Alice is the name of the experiment. And you can think about it as a kind of a big camera that takes a picture of how particles collide with each other. And they do it at an unprecedented frequency of terahertz, of order of terahertz, which means that this is actually a lot of data being captured. And now under the hood, there's machine learning going on. One of the algorithms that we developed was focused on analyzing the quality of this data. And if you do it quite well, you can basically skip some of the corrupt data to be saved, hence leading to efficiency increase and also reduction of storage. So that's quite often used machine learning algorithms in this context as well. And third, probably closest to all of us, is the deployment of autonomous cars, autonomous vehicles, and agents all over the world that we can interact with. In those applications, especially those of critical latency, such as cars, machine learning and saving on a computation done by machine learning can be of a big importance, saving some time before finding out that there is a kid playing ball in front of the car can actually save his or her life. So these are the three motivations that I usually give when it comes to the research on increasing efficiency and zero waste machine learning. Now, to give you that perspective of how it translates into number, let me say first that the amount of electricity that is consumed by data centers all over the world was estimated for 2024 at 415 terawatt hours. That's approximately 1.5% of all electricity worldwide, and it's supposed to double by 2030. So it's a huge amount of electricity that we use to run machine learning algorithms. Now, in comparison, our brain every day uses around 600 watt hours. Looking at 150 kilowatt hours of Tesla 1000 kilometer drive, that's not that much. But if you compare that with 190 megawatt hours, which is an estimated GPT training, this is a huge increase of energy needed for training our machine learning algorithms. And GPT-3 is not even the newest one, the newest model that we can play with, and with OpenAI or Gemini, etc. So that 190 megawatt hours can be converted into 85 tons of CO2 emitted, of course, depending on the energy mix that your electricity provider offers. But this is roughly comparable with 1,200,000 kilometers drive between using a combustion engine car, which is around 4 times the distance between Earth and Moon. So these are the numbers that give you kind of a perspective of how important looking at efficiency of machine learning algorithm really is. Now, this especially becomes important in countries where not enough energy comes from green resources, from renewable resources. In Poland, for instance, between 30 to 40% on average comes from renewable sources, while the rest is usually fossil fuels. So that impact we can observe not only in terms of the consumption of energy, but also in terms of air pollution is significant. Now, most of the people that find this problem would start with saying that, well, you can just, make those models smaller. You can shrink them. You can quantize the weights, and you can distill the knowledge from those models, like DeepSeek did. And as a result, you would obtain a smaller models, more efficient, etc. Now, this sounds quite sensible. However, if you look at the graph, if you look at the numbers and if you see how the parameters of the models, how the number of parameters of the models we publish grow, and they just swell too fast. So even if you are able to increase the efficiency or to quantize those models, but the models are just exponentially larger every year and so on. So that's not enough. We need a different paradigm. We need some sort of a change in the way we reason about models. And this is what we think of in terms of zero-waste machine learning. So the first group of approaches which we researched in the last couple of years is based on conditional computations. And this means that you condition the output or condition the processing of the information with a neural network based on the input. If you are in the forest and you take a photo and you want to do image recognition, you most likely will not see any skyscrapers. Therefore, part of the network, part of the model that is relevant to recognizing objects from city are not supposed to be activated. This is just one example of how this can be done. I give you a brief introduction on the methods we pursued, but that's the first group of machine learning methods we follow in zero-waste machine learning. The second pillar of zero-waste machine learning is knowledge accumulation. So what we do is we accumulate knowledge within our models. We kind of pack the world around us and models that evolve with us. We accumulate that knowledge rather than retrain the models from scratch. This also bears the name of continual learning, which is quite often referred to in the literature as this way of simulating how humans or how animals learn. So we don't actually learn every 2-3 weeks everything from scratch. We accumulate knowledge. We learn what is more relevant, less relevant. We forget parts of what we don't use, but we also are able to accumulate new information and learn new skills and new information. So this is what we try to do with machine models, which by definition do not have this skill, and I will share in a few minutes why. And then the third pillar for us is looking for inspiration in real life use cases. So platforms such as drones or mobile platforms or edge AI devices give us the best inspiration for where zero-waste machine learning is actually quite useful. So these would be like 3 groups that I will try to cover today during our talk, and I hope that you'll find that interesting. All right, so let's dig in. First, the conditional computations approach. Let's look first at one of the simplest way you can think about models. So you see the image in the beginning, and then it's kind of processed through the network from layer to layer. And if there is some sort of confidence getting from the middle layers, you could output the results, for instance, the label of dog, even without going till the end of this processing pipeline. This was proposed in 2019, and the intermittent classifiers, the IC modules that you see in the slide, these would be actually quite efficient early exit approaches, and this is the family that we got inspired by, and we started looking into it. So what we did is we actually looked at how much information is being discarded rather than reused when this kind of processing occurs. And we asked the questions, well, actually one question: do early ICs know something that later ICs do not? So in other words, we tried to identify how much information is being lost and wasted within the processing with early exit networks. So to measure that, we came up with a metric. First, we look at the set of correctly classified samples for the mth IC. We measure the number of incorrectly classified samples. And we look at the overlap of those with the situation where the previous classifiers, previous intermittent classifiers were right. So when you get to classifier, let's say number 5, you measure how many of the previous ones were actually right before getting to classifier 5. Would classifier 4, 3, or 2, or 1 give you the good answer? And we measured that with hindsight improbability, a metric that we came up with that shows how much of information can actually be reused and whether we can save some computation by looking at previous ICs. And so the answer to the question we asked was that yes, we can actually use some of the information being wasted. The hindsight improbability for ResNet 56 on Cipher 100 was actually reaching around 70%, which means for the last ICs, we could save and we could reduce the mistakes by 70% if we are able to perfectly reuse past information, which is what we propose to do. So instead of looking at every single layer of the processing pipeline one by one, we came up with a method to connect intermittent classifiers. So add this additional pipeline, additional connections between them. And in this way, the former IC responses were used and were being input into the latter ICs, and therefore we prevented the network from wasting resources that were already spent on computing computing the output. This was the paper we published at NeurIPS 21, and zero time waste it was called, and it kind of sparked this idea of using zero waste machine learning as a fundamentally different paradigm to saving computations and increasing efficiency. So how does that work in more details? First, we connected the components, the ICs, with a fully connected layer at the end. This was the cascading part, which you see in red here. And then we used aggregation method that was geometric mean that allowed us to basically increase, to basically take into account the previous responses. We tried with other types of means or averaging, but the geometric means seemed to be the one that worked the best. And as a result, we observed quite a bit of improvement, especially when measured against inference time. So on x-axis, you'll see inference time, which is with respect to the baseline method, base network without any intermittent classifiers, without any skip connections, was 100% and accuracy of around 0.7. Now, the base method that we compared with SDN, so the one early exit method that does not have any connections between ICs, is depicted in blue, and our in yellow actually improved not only the efficiency, and you can see it by looking at the yellow plot, but also we got better results, which means that we were able to improve the accuracy by taking into account the information pre-computed by previous intermittent classifiers. So as a result, we seem to be actually getting better. Now, another approach that is quite often used in conditional computation is called mixture of experts. These would be even more recent models that you can see nowadays in Google Pathways approaches, and also in big large language models. So the goal here is to train larger models, but with fixed compute size. And how do you do it? You come up with a model where there is a routing gating network that indicates which part of the main space model is activated for a given input. The parts of the model that we refer to here are called experts, and they are in practice sparse feed-forward networks. So this was proposed in iClear 2017, already quite some time ago, but it wasn't actually used in the context of saving the compute. It was more used to train even bigger models than we were able to fit on the memory. Now, we looked with more details into how the activation is distributed in transformers that are trained with a mixture of expert approach. And we observed that, of course, the higher activation sparsity, the more computation we save. The more sparsity means that less or smaller parts of the network is activated. But the cost of that was that the variance increased after sparsification. So basically, a different number of experts was needed to replicate the original activations. So you cannot actually use the same number of experts every single time you observe an input because of the variance. The responses are just too diversified. The variance is just too high. So what we proposed in 2024 is a dynamic k-expert routing. This was a NeurIPS paper where instead of using top k gating with just a fixed number of experts, we moved to adapting the number of activated experts based on the difficulty of the input. So as an example, you can look at the top right corner here, and you see that the cat in the abstract version of a cat activates 2 experts, and obviously it's not appropriate. I mean, the cat image is just much closer to the training data, while this abstract version of cat seems to require much more thinking. And this is what we proposed. This is the bottom picture. We proposed to dynamically adapt number of experts. For the cat picture, just 1, and for the abstract version, we can scale it up to 4, so pretty much the entire network based on the difficulty of the input. The approach we proposed, D2D MOE, so D2D mixture of experts, consists of 3 parts. First, we enhance the activation sparsity in the base model. Then we convert the feed-forward network layers in the model to a mixture of expert layers with routers that predict the contribution of each expert. So the routers are actually trained to predict how much we need to involve each of the expert, and that gives you the L2 norm of the magnitude. And then we introduce this dynamic k-routing that selects the experts for execution based on their predicted contributions. So we just cut off the contributions and then choose only the experts that are above a certain threshold. And this approach allowed us to basically increase the efficiency of our computations. As you see here, the blue curve increases or keeps within the same accuracy, keeps the G-flop number, so the computational cost of running the model much lower than zero time waste, ZTW, as well as modification, which is another baseline we compared our approach against. Now, we also looked at expert utilization maps. So we wanted also to verify if this is true, that the experts themselves then focus on certain parts of the image that are truly more complex, more difficult to analyze. And for instance, you can see here how the corkscrew is being identified in the computational load maps. And if you look at airplane image here with a blue sky, of course, the experts focus much more on this element that is flying rather than the sky itself. So this was pretty much it for conditional computations research. We still continue this path. We've got some few new papers at the last NeurIPS and got accepted to iClear. But now let's move on. It was just a brief kind of overview for you to get your head around the computational conditional computation topic. Now, the second pillar of zero-waste machine learning is knowledge accumulation, as I mentioned. And to give you an introduction to that, let me first explain what continual learning is. And this is very much relevant when it comes to thinking about how machines learn, how machines are trained, versus how we humans or animals in general are learning. So in continual learning, the assumption is that you have input x1, the data set with labels y1, and you train a model, usually a neural network, that assigns those labels to the input data. The neural network remains the same, but now data changes. And now instead of x1, you have a new data set x2, which can be completely different from x1. And also you want to do the same, assign the y2 labels to x2. This, in turn, when time comes, can actually be further expanded into infinite number of data sets, and you can think about data in this approach as a stream of experiences rather than data samples. So this is what you can think of as an example of why this is difficult. For us, it's not difficult. For humans, it's quite natural that you actually observe the world around you, and you trained how to ride a bike, and then you move on, you grow, and you learn how to drive a car. You don't forget how to ride a bike when you start driving your car, right? So that's usually what happens, but for models, it's not. What they do is they catastrophically forget what was taught to them before. So if you present a data set, let's say MNIST for simplicity, that contains all the numbers from 0 to 9, you'd quickly get to now almost 95, 97, 99.9, depending on the model accuracy. Now, when you split that data set into, let's say, 5 subsets, task 1, task 2, task 3, and so on, and you feed the model sequentially with those smaller data samples, the smaller data sets, or subsets of the big MNIST data set, then you can sort of simulate what happens when data is changing. And this is what you see here in the curve. You first see that the blue curve, which is the accuracy for the first task, goes almost to 1. But when the data set is changed, when the training data set becomes new, then it suddenly drops, and the task number 2 becomes more accurate. And the same goes on for the next set. So basically, the model forgets, and it forgets catastrophically what it previously learned. Now, this is to be blamed to gradient descent. If you think about what neural networks model actually do, they find the minimum of loss functions. And now, if you look at this landscape of loss function within a given data set, let's say that it's the task 1 that you analyze first, they would go towards the minimum of the first landscape of the loss function. So that would be task 1 on the left. Now, if you move this, if you change the data set, all of a sudden, there is a new minimum in the right. There's task 2 solution that you see on the right. And then the network moves from the first to the second minimum. Now, this is a completely different place than what you would get to, and different point from where you would get to if you combine those 2 data sets. If you see during optimization both data sets from task 1 and task 2. Therefore, you cannot expect the model to behave similarly when you split the data set into smaller chunks and then you go one by one. So this is not this is not a new discovery. Actually, continual learning is a way or a bunch of methods, a stream of research that was going on for the last decade or so. And we've already seen several approaches evolve. First, regularization, so trying to keep the model as close as possible to the previously trained parameters. Second of all, architectural, so you basically build a new elements, new modules of your model, adding the complexity of processing, but then you can think about that as additional head for a given task that is being associated with the model. And then two similar, but a little bit different from the rest, approaches based on repeating samples from the past. These are the rehearsal models, rehearsal methods that repeat what a model has seen in the past from a data buffer, from data sample buffer, and generative replay, which does pretty much the same thing, but regenerates samples using generative approaches. So generative models such as GANs or variational autoencoders or diffusion models. Now, the rehearsal is what seems to be working quite well, actually, especially when combined with distillation. But just to keep it simple, let's put it this way: it's like us dreaming and being reminded about things that happen during the day. This is how our brain encodes information and puts it through our neurons. Similarly, here, models are performing very well. They're kind of counteracting the catastrophic forgetting when they can repeat some of the past samples from a buffer. However, the limitation is that to keep all the information from the previous runs, you need to increase memory infinitely. And that's, of course, not ideal because you need more memory, etc. It's becoming infeasible. So that's where generative models came into play. That's where the generative rehearsal was introduced. And these were pretty much variation autoencoders and generative adversarial networks to start with. Now, this hypothesis that we had when looking into those models was that generative models are simply more robust to catastrophic forgetting because their goal is to represent the data rather than discriminate between instances. So if you think about that, it's much more powerful of a representation that they learn internally than the one that you need to discriminate between cats and dogs. We had a paper on that in 2021 and then followed up on this work. We specifically looked at variational autoencoders, as you can very easily detect which part of this model is to be blamed for catastrophic forgetting. And we built this understanding of what's the problem with variational autoencoders trained continually. So if you train your model first with cars and then you train the model with horses, you would see that the continuous latent space, the Gaussians, the distributions within this continuous latent space will start to overlap. And then as the output of this model, you will get some blurry images of something between a car and a horse. And then the regenerations of the previous samples will slowly start to degrade. And this is what we observed, and this is what we try to overcome. And that's why we proposed multiband variational autoencoder. In 2022, at DeechGuy, we published a paper that proposed to use an additional element of the standard variational autoencoder pipeline, which is local encoder, local decoder. So that's the usual way. But we ask a question whether we can actually align data from consecutive tasks in the latent space. So whether we can actually pack the latent space according to our needs. And we cast the knowledge accumulation problem as a latent space partitioning task. And for that, we used a translator, which is an additional module over here, which moved the data from the representation, internal representation learned by a local encoder within a given task to a global decoder with aligned latent space as a result. And to give you kind of an intuition of how it worked, let's look at this example again on MNIST, but first on top you'll see generative replay, so a standard baseline approach where in the task number 1 you have classes you have only one class only once, and then in task 2 you introduce class 0 of the letters, and you start to see that the ones and zeros are actually getting blurred, like zeros are becoming more and more close to ones, and vice versa. And now in the third task you introduce a class, another set of samples from class 1, which the model has already seen, and a new class 2. And then this is where the hell breaks. You see there's no alignment of ones, there's some data degradation from the previous samples, and the model starts to really collapse. Like you're not able to use that model to generate previous samples anymore. Now, in our case, for the approach we propose, which is multi-bar variational autoencoder, you see the instant separation of the classes from the second task. And then in task number 3, you see that the same class, the ones are aligned with each other, and the 2 and zeros are actually separated in this space, which is exactly what we were looking for. Now, we looked at another problem and another way of approaching this catastrophic forgetting, which is the internal representations of neural nets, how they're built, how they behave when you give them consecutive data sets. And so we looked at a random 204th dimension of the latent space. And we saw that there are 2 different distributions. The probability density of the activations is different for 2 classes, cats and dogs. Let's give it as a sample. When neural nets forget, basically the distributions start to shift, start to move around. And this is where the forgetting comes from, and this is where the forgetting is visualized in this case. Now, we thought that we can replace the classification head with base classifier. And so we came up with the divide and not forget approach, where we trained expert ensemble as a method of building a classifier on top of the activations of a deep neural network. So in this case, if you look at experts 1 and 2, these are specifically 2 parts, 2 modules of a neural network. They internally built some representations, some distributions of activations for a bunch of classes, 2 classes in this case. Now, when the task number 2 comes, they built another type of another set of distributions. Now, for the task number 3, where we have new distributions coming in, we look at the expert that will give us the lowest overlap between the distributions if we create those, if we use this expert to encode the information about new classes. So we select the one that has the least overlap in the latent space, and then we fine-tune this expert to further increase the separability of new classes, as we did for multi-bar variational autoencoder. When the inference comes, we look at log likelihood and softmax, and we make an average of that and choose argmax. As simple as it is, we published that at iClear 24, and it actually gives a fairly good result when it comes to reducing catastrophic forgetting. Now, the last group and most recent, I would say, of the continual learning methods we are looking at these days is based on model merging. So you see foundation models, they allow you to build from the blocks some new approaches of new models. And in 2023 at iClear, there was a work that showed that editing models can be thought of similarly to arithmetic operations. So task vectors are defined as the vectors that move one distribution of the weights to another. And if you want to negate, like basically make a language model produce less toxic content, you train a model, then you make it more toxic, and then you turn the vector, the task vector, around, and you change the weights in the other direction, making it less toxic. So you kind of identify the arithmetic that you can do on those task vectors. This is also helpful when you want to learn multitask models. So you want to learn via addition, or you can find task analogies like improving domain generalization. Now, we observed that parameters that change the most during fine-tuning are the most important for the task. And we looked into that when we were preparing our ECCV 2024 submission. And what we came up with was MACMAX, a paper, an approach accepted at this conference. So what MACMAX does is a very straightforward method, quite simple actually. We first sequentially fine-tune our model for a set of data, for data subsamples, for a set of data splits. We construct task vectors for every single of those fine-tuned models, and then we select highest magnitude candidates, combining that into a task vector merged and applied on the base model. Now, merging those models through task vectors seems to be actually working surprisingly well across different classes, across different data sets, and outperforms the majority of the baseline works we actually compared against at that time. So this is pretty much it when it comes to the second pillar of zero-waste machine learning, which was knowledge accumulation. Now, for the last few slides, I'll give you an example of what we mean by real-life use case inspiration. And for that, let me just play a short video showing how humans and machines look like, or look at the world around us. So human kind of concentrates their focal, the view on a central point, while AI or machine learning models actually scan the whole thing. The whole image is basically analyzed from left to right, from top to down. Now, the problem that we can come up with after looking at those differences is where to look next. This was the setup of the ICCV workshop 2919 by Tina Tutilars and her PhD student. The question they ask is, can we take a few glimpses of the image, not look at the entire image, but just take a few glimpses like humans do, and then reconstruct the entire image of the bridge in this case. And the problem is, what is the sequence of those glimpses that you have to take to get the best results? And this is basically how it works in practice. You see the input being a set of glimpses, one after another, showing up in your model. And what you do is you try to predict the best reconstruction. And you can see already with a few samples, few glimpses, you can pretty well reconstruct the entire image. Now, this was the problem that was solved in this paper, but through an additional glimpse selection loss. So basically, there was a target task loss proposed and a glimpse selection loss. You optimized two losses. What we thought, according to zero-waste machine learning principle, is that perhaps we can use some internal state of the model, like the masked autoencoder state, to save on computations and do not look at the glimpse selection loss. Just focus on what we already have available at hands. And that was the reason, and that was the approach we presented at HCAI in 2023, active visual exploration. So what it offers, what it proposes is to use attention map as uncertainty estimator, basically divide image into 4 patches, and then compute the attention maps of those patches, and then compute Shannon's entropy on rows, and choose the next glimpse to be the one with the highest entropy, given that it probably has the highest amount of information required. So as an outcome, we showed we were able to basically reconstruct the images with the best result compared to the other approaches, which were much more blurry, as you see, with only 5. I think this one is only 5 patches that we need for 5 glimpses to reconstruct the whole image. And the problem, the limitation was that those glimpses were supposed to be grids or aligned with the grid. We came up with a method to make them more elastic. So instead of just keeping them as one size, we added the component which allowed the scale and size of those glimpses to be different. And that's where we came up with a method, glimpse, published at ACGV 2024. And yeah, it worked flawlessly. You can see in the qualitative analysis that it actually focuses on the right elements of the image to make a decision about the class of the objects it sees, and it provides actually best results out of the ones we evaluate against. So to wrap up, this would be like 3 pillars that we spend our time on building the zero waste machine learning paradigm, and we are exploring pretty much all of those paths right now. Like, I'm in a slightly different capacity, but I believe that this can give you an inspiration of how we can think about models and the computations we already have, the state of the models we already have at hand, to save computation, to increase efficiency, and in the long run, to basically not waste the stuff that we already have at hand. So just to say thank you, it's not only my work. Of course, I have a bunch of PhD students and collaborators from different institutions, and also this work was supported with a bunch of grants coming also from European Union, as well as Elias grant, which is a part of the effort within Alice Network. And then I think this is it from me. If you have any questions, I'm happy to take them, and feel free to explore Alice Unit Warsaw if you're interested in other work coming from our unit. Thank you.
Yeah, thank you very much, Tomasz. And so we have a few questions in the chat. The first is, in the era of foundation models, is research on continual learning still relevant?
Yeah, that's a very good one. So the model merging approach that I proposed is actually going along the lines that foundation models are available. What foundational models offer is that they are trained on big data sets that are considered to be representative enough so that any new data coming in can kind of bears similarity to the data samples that the model has previously seen, which means that effectively you don't observe that much of a catastrophic forgetting. And this is the notion that a lot of researchers in the community kind of understand and also agree with. But there are still certain cases where availability of foundational models is not there. Like, for instance, if you travel to outer space, if you try to implement your model on an edge device that is trying to analyze the samples of rock in some other galaxy where there's no information available about what the objects look like. And in this case, the situation is still the same. Like, you have to come up with a method that can gradually adapt to new information, and you have no guarantees that the model is able to collect the data or to access the data previously collected. And especially compared with foundation models, it has to be fairly compact. So I would say that it's probably less of a relevance these days when it comes to standard applications, but there are still use cases where continual learning and knowledge accumulation is quite of importance.
Okay, thank you. And what recommendations would you offer to users regarding the consideration of energy consumption in ML models?
So that's a good question. I would say that especially for users or for researchers, people who are on a daily basis talking to chats and then talking to LLMs and then basically trying to use those models in their everyday job, I would recommend to look into the energy consumption that those models offer. It's not an easy task, but you can actually get that out also as an estimate when talking to ChatGPT or Gemini or Claude. And basically be aware of the decisions that you take. So for instance, if you're being polite to ChatGPT or Gemini, and if you thank for the answer it gave you, you're actually increasing your carbon footprint by generating additional set of tokens and also asking the model to process them. So I would say be aware, find the information, and then if you're, if you want to be considerate about the impact you have on the energy consumption, on the energy our planet is producing, and the consumption of data centers, as I mentioned in the beginning of this talk, which is humongous. And then just at least think about that, like we think about, uh, appliances, kitchen appliances. When you buy a fridge or when you buy a washing machine, you have usually some sort of information like from letters or some taxonomy of the energy consumption. Now, for models, we don't have it yet. I know there is some EU work. The European Commission is working on some acts to kind of make those decisions more available for the users and available for people, but it's not there yet. So I would recommend for you to make that effort and think about this, and then based on the outputs you receive, try to make a decision of your own.
Okay, and thank you very much. And the last question, Thomas, is which applications of your methods do you regard as the most important?
So for us these days, I think the most important ones are those related to low efficiency platforms, those that are like drones or mobile phones or the edge devices. So this active visual exploration is one of the method that we actually test on battlefield. We test that in security applications, like security and basically the situation, the geopolitical situation makes us much more aware of where the models can be used for good, in a sense, right? I mean, I'm probably if you asked me 5 or 10 years ago whether security is important and whether we should think about dual use of AI technology, I would say that it's not really, ethical or moral, etc. But given the situation and given how the geopolitics change, I believe that these are actually becoming more and more relevant for us these days. So how do we actually protect ourselves? How do we invest in the applications that can offer us security, be in the position that we can increase our security as community and as society. And in general, I believe that edge AI and implementing machine learning models on devices that are closer to us, from doorbells to autonomous cars, and this is super relevant and this is super important. Like computing models and computation of LLM responses in the cloud is very sexy. People are really excited about this because it changes, it provides this paradigm shift in how we think about future. And then, general artificial intelligence sounds really cool. But what we observe in our everyday life, what impacts our life the most, is those tiny little models that are helping us every step, where to go to the nearest pharmacy, how to avoid falling over because there's some ice detection, and how not to let intruders into your house because they were detected as potential burglars. So these are the tiny little models that I believe will have a huge impact, and we want to contribute to this effort as a researcher.
Okay. Yeah, thank you very much. And for your talk, and also
Thank you.
inspiring Q&A. And yeah, looking forward. And thanks again for attending our Molecules to Model Alice webinar series today.
Thank you so much for the invitation. It was a pleasure.
Thank you for participating in today's AI for Good session. We hope you've learnt something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the e-shop, and build your personalized AI for Good program. Let's shape the future of AI for good.